All right, this section is about limits at infinity. When I took Cal 1 ancient years ago, I remember just battling this concept. The word limit and the word infinity did not belong together as far as I was concerned, and I just fought that. It was like, you can't have a limit at infinity. Infinity goes forever, and so I just refused. I just had a block. So we're going to hope that we can get beyond that, because there isn't a number infinity. There isn't a number that equals that. So when it says, like if it says the limit is infinity, what it's really saying is there isn't a limit. It doesn't exist. We're talking about the behavior as it reaches something. It's like it goes forever without reaching something, but we call it, sometimes we'll say the limit is at infinity. It's really not a number, and it really doesn't work that way. So there's two rules in this section that are important. You do need to know these. You're going to have to know them for the test. The limit as x approaches infinity of 1 over x is equal to 0. Or if you approach negative infinity of 1 over x equals 0. Let's think about what that's saying. All right? As you go to infinity, what does that mean about your numbers? What are they getting? Bigger. Okay. So if I start out with 1/2 and go to 1/3 and go to 1/4, 1/5, 1/1000, what's happening to my value? It's getting smaller. So if I go to infinity, I'm essentially getting extremely close to 0. Okay? So that's what that means. The limit as x approaches infinity of this expression is 0. Okay? And sometimes that's hard to think about, but that's what it is. There's a technique for finding the limit of rational functions as x approaches infinity. And the technique is you're going to divide everything in the top and everything in the bottom by the highest power of x. So here's a problem. If we had the limit as x approaches infinity of 5x squared plus 8x minus 3 over 3x squared plus 2. Okay, well, it's not like regular limits where we can plug in a number. We got to have some technique. The technique is, what's the highest power of x? X squared. So every single piece of this gets divided by x squared. So I wrote it all out. 5x squared over x squared plus 8x over x squared, blah, blah, blah. Okay, so that's what we do first. Then we start simplifying. 5x squared over x squared becomes just 5. 8x over x squared becomes 8 over x. We have 3 over x squared. 3x squared over x squared just becomes 3. And 2 over x squared, we're there. All right. This needs to look familiar to you. It doesn't matter whether it's 8 over x. That's the same as 1 over x as far as the rule. So each of these pieces we kind of evaluate then. The limit as x approaches infinity of a constant is going to just be the constant. So we have 5. What does this one go to? 0. This one, it doesn't matter if it's x squared on the bottom or x cubed. X to any power. If you have a number on top and x to a power on the bottom, it's going to go to 0. So 5 plus 0 minus 0 over 3 plus 0. The limit is 5/3. The limit is 5/3.
One more time, why does it go to 0?
That rule up here,
Oh, okay.
that rule. Okay, so the limit as x approaches infinity is 5/3. Now what I want us to do is look at this expression in the calculator and see if this is holding true. See if it seems like as we go this way on x, we're going to approach 5/3. So we're going to go to our calculator and we're going to put this thing in. So if we do that, we're going to have y1 equals 5x squared plus 8x minus 3, close, divided by 3x squared plus 2, close. Bless you. Is there something else going on over here? No. Does yours not look like? What did I do? Oh. Okay. I knew something was wrong there. Okay, I think if I do there and do insert, is it going to work? Hopefully. Maybe. Okay, is that what you got? Okay, so let's think about it. As x approaches infinity, as we go all the way there, what is the y value about there? It should be about 1 1/4. So if I went, let's do second, let's change the window. Let's change the window and make x max 200, just to get over on the right. Okay, so it looks like it's kind of evening out, and probably 5/3, so 1 2/3, I don't know, probably right about there. We could check that. The value, let's do second calc value, and let's put in not 200, let's do 199. Oh, let's do it right. Yeah, 1.68, is that about 1 2/3? Did you get that? Or something like that? So as you're going that far on the graph to the right, you've kind of got this limit that it's not going to go over. Do you know what that's called? What's that called when you have this kind of a barrier? Asymptote. So as you approach infinity, the limit at infinity is a horizontal asymptote. In algebra, in pre-calc, we did it where we looked at the numerator and the denominator, and we came up either y equals 0, y equals the coefficient over the coefficient, or there wasn't one. So in this case, the limit as x approaches infinity is 5/3. That's the horizontal asymptote. Okay? And you could do that algebraically the way we did in college algebra. Some of you, a few of you had me for college algebra. But you would look at what's the degree of the top 2, what's the degree of the bottom 2. So the horizontal asymptote was always y equals the leading coefficient over the leading coefficient, which is 5/3. That's the algebraic shortcut. That's not finding a limit, but that's the way to find the horizontal asymptote. They are the same thing. Okay? All right. So let's look at that one. As we approach negative infinity, it's the same way. We're just going that way on the x. 11x plus 2 over 2x cubed minus 1. So we're going to divide by what? X cubed. So I did that on every piece. We get 11x over x cubed, 2 over x cubed, etc. And then we kind of clean it up. 11 over x squared plus 2 over x cubed. And then that becomes 2, and then we have minus 1 over x cubed. Those both go to 0. That goes to 0, so I have 0 over 2, which is 0. Okay? And we learned in algebra, if the degree on the bottom was bigger than the degree on the top, the answer was y equals 0 for the horizontal asymptote. So it holds true. Okay?
What if those are switched, like in the 2x was on 2x to the third one on top?
You would not have one. You wouldn't have an asymptote, so you wouldn't get this. They're not going to give you one like that. Okay. All right. And this was just a reminder. I'm going to skip that part. But horizontal asymptotes right here. I reminded you about the algebraic rule here. So that's there in the notes if you need it. Okay? So really, a lot of this is just algebraic working, dividing by the highest power of x, and coming up with the limit. Okay? We good? All right. Let's look at problems. Okay. I don't know why I didn't make those big to start with. All right. Select the correct choice. Okay. The limit as x approaches 6, I believe, is what? Can you see that? -4. All right. The limit as x approaches -1 from the right. -1 from the right. -3. Because here you're at -1, and as you go that way, the graph's doing this. So then you end up at -3. Does that make sense? Okay. The one at... Okay, yeah, because you have to, you're coming this way, and so the only piece that's coming that way is there. All right, let's look at these. Oh, real big. Okay. I guess this is still on that little picture. So can you keep that in mind, and I'll read maybe. The limit as x approaches -1 from the left. So as we come in -1 from the left, where's our graph? 6. So that's at 6. And then the limit as x approaches -1 does not exist because from the left it's here, from the right it's here. So it does not exist. Whoops. This one. Why could I get an answer here? You're just coming in from one side. Okay, you can have a one-sided limit. You cannot have it in general because it was different on both sides. All right. Let's see what this guy is. The limit as you approach 4 from the right. 4 from the right. Where are we? -4, right there. Okay, and the... Okay, we'll go down and write that in. I'm so sorry. We have to... This is good. This is why you should have the sets in front of you. Okay, next part is... Okay, 4 from the left. As we come in at 4 from the left, where is the graph going? Infinity. Okay, so that one's infinity. We'll remember that. As we approach x equals 4, in general, does not exist because we got infinity on the left and we got -4 down there. So let's go fill those in. So we said this was infinity. A little icon. Yes, it may be, if it's not on those original ones, there's a little button that says more, and it's in there. Okay, I can't remember for sure. Oh, okay, it shows up. Okay. H. Where's H? All right, the limit as x approaches infinity. Okay, let's look back here. As x approaches infinity, so as we're going this way, where's our graph approaching? -2. Okay. And as we approach negative infinity, +2. Okay. All right. So that's that. Okay. All right. Number 2. That was a long number 1. All right. Find the limit of f of x equals 7 over x minus 12 as x approaches negative infinity. And so this is where we have to remember limit as x approaches negative infinity of 1 over x equals 0. So what's our answer? Negative 12. Okay, because this, the limit of that is going to be 0. And then you just have the negative 12. Okay, we good? I don't know why I didn't make these bigger to start with. Okay, we got this business as we approach positive infinity and negative infinity. Okay? What do? Do we have to do anything? Can we just evaluate? Is this one going to be negative 6 plus 0 over 6 minus 0? So what does that become? Negative 1. So negative 1 here. Will it be the same for negative infinity? Yes. Okay. Because the rule stands for both positive infinity and negative infinity, so it won't change your numbers. Okay, let's do this one. Find the limit of this as t approaches negative infinity. Okay, so what am I going to divide by? Got to remember a couple of things. What's that rule we got last time in class? Sine theta over theta equals 1. Okay. All right. Equals 1. Okay. I went blank for a minute. Okay. So what are we going to divide by? What could we divide by? 9t. So if we divide everything by 9t. Let's see if you do that one and see if you can come up with the answers right there. So let's see if we can come up with that. Okay, so we looked on the calculator and we could see that as we're approaching infinity, that expression, sine 9t over 9t, is going to go to 0. So now we've got 0 minus 5/9 plus 0 over 6/9 plus 0. So we've got infinity. I think so. I think so. And that's what I was thinking we were going to discover. Yeah. Yeah. So you have negative 5/9 times 9 over 6, which is negative 5/6. Okay. So we're good? Yay? Okay. Did you get it?
Yeah, but I just wanted to, like, how did you get, when you put it in the calculator, how did you decide to sine 9t over 9t?
Well, I knew these other pieces would go to 0, and we hadn't talked about this piece and why that might work, so I wanted us to look at it. And so we do what? Okay. When you go to this graph, can you see that that's getting smaller, 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 smaller? So as you go to infinity, as you go to bigger, bigger numbers, x, what's going to happen? It's going to be tinier and tinier and tinier. It's getting close to 0. A y value of 0. Okay, is that better? Yeah. Okay. All right. And Leland, what was your?
Well, I'm just, like, what I'm saying is, you're saying that goes to 0.
That piece as you go to infinity, which we can see just that piece in the graph. That's what I wanted you to see, that as you're going this way, you're getting closer and closer to 0. If we changed the window and made the x max.
Well, so what if you put the other ones you have highlighters in there.
If you put that piece in,
Yeah.
you would get the same idea.
Yeah, that's good.
Yeah. Yeah, you would if you tried it. Okay? And a lot of times you can visually see the limit when you can't maybe remember the algebra of it. So it would maybe prompt you. So you do want to use your calculator for visual help sometimes. Do what? Yes, yes, absolutely. But that wasn't quite the same deal. It looked different. All right. Here's this one. Find the limit of the rational function as we approach infinity. So, and it's kind of a multiple choice, but let's see if we can come up with, if you know your algebra, do you know what the horizontal asymptote is before we start? 11 over 4. Because these two are the same, x to the fourth and x to the fourth, so it's leading coefficient over leading coefficient. But if you had to show the work of how we're doing the limit, we got to do that. So what would we divide every term by? X to the fourth. Okay, so let's just do that. So which of those pieces can cancel out? So like we can do that and that and that, and then what happens to these two pieces? They go to 0. So we end up with 11 over 4. Okay? It's kind of nice if you remember the algebra rule because you know the answer before you start. If you have to show the work, you've got that. Okay? Any questions on that? Okay, that rule, Jeff, if we simplify this, we get 20 over x, right? Because x cubed cancels out with x to the fourth. And so any number over x or over any x to any power, that rule says the limit as you approach infinity is going to go to 0. Because as x gets cubed, 20 over 1 million, whatever, what happens to that value? That value gets infinitely small. So anytime you can reduce them to that, then you get, I thought we had alarm, then you'll go to 0. Okay? All right. All right. Let's try this one. Do you know algebraically what the horizontal asymptote should be? What? 0. Because the degree on the top is smaller than the degree on the bottom. So it should be y equals 0. But let's do the work and come up with 0 as the limit. Yeah, yeah. So that's going to equal 0 there, 0 there, 0 there, 5 on the bottom. You got 0 over 5, which is 0. Okay, so it helps if you remember the algebra rules because you know where you're headed. You know whether you're right or wrong maybe before you do it, because if not, you might not be sure. Okay, questions on that one? Okay, all right. The next one has a good bit of algebra, and I want everybody to work it. I'm not going to work it right away. It's going to be a good one. Of course, I guess that's a matter of opinion. Doesn't that look ugly? Leland says no to that one. All right, here's what I would suggest. I would rewrite the problem. X to the 1/5 minus x to the 1/8 over 2x to the 1/5 minus x to the 1/8. You don't know what means?
What the little, like the radical with the, yeah.
It's an index, like it's saying the 5th root of x, and there's always an understood 1 there, and when you change from radical to fractional exponents, that's your numerator, that's your denominator. So that's where we're going to rewrite it this way. It's going to be easier.